Cool. Okay, I think we should get started. So that we have time for everything. So I guess I'll introduce Shoumik. So I'm really, really excited to have Shoumik do his defense today. He's basically the first student to start working with me, so that's awesome. And he's done a lot of really great things in systems and a bunch of other stuff, like some security stuff on the side and a bunch of other things as well. So I think I'm obliged to say some embarrassing story about Shoumik. So Shoumik started with me in 2015 when I was at MIT. And he had been, had been in Berkeley before, and his family was in the Bay Area. And so he came to MIT, he was doing great, but I noticed that he was spending a lot of time going back to the Bay Area. And I was wondering why. So he would say, oh, can I go to this conference that's there, even though I don't have anything to present, I'm just really interested in the research. And so he went to a conference there. And then after that, he said, oh, can I stay another week after the conference? Because my family lives there and stuff. And this kept happening. So I was wondering, why is it? Maybe he really misses his family? He lived in the Bay Area all his life. Maybe it's like a big adjustment. Maybe the winter is gonna get him, and he's not gonna want to do stuff at MIT. And then at some point, I had kind of this chance to move to Stanford and to be back in the Bay Area. And I asked him like, hey, I'm thinking about this, but I'm not sure I want to do it if it's going to mess up all the students who started with me. So like, would you be willing to move back? And he said, yes, he'd be willing to move back. And it turned out that the reason he'd been going back a lot is because his girlfriend, who he met just as he was doing grad school visit days, was in the Bay Area, and of course she's now his wife. So they just got married. So that's one story about Shoumik. But that was just one mystery, I guess, that I eventually figured out. Maybe everyone else knew, but I didn't. So with that in mind, I think Shoumik, you can go ahead and present.
Cool. Yeah, thanks for the intro, Matej. Yeah, just to reintroduce myself, I'm Shoumik. I'm a PhD student in the Dawn lab working with Matej. And I'm going to talk about my dissertation work on interfaces for efficient software composition on modern hardware. All right, so software composition has been a mainstay in computer programming for decades. In fact, pioneers of computing such as Dijkstra and Sussman have written papers and books about how programmers need to modularize, reuse, and compose existing code in their own applications since the 50s and 60s. So the result of this has been an explosion of fast, robust libraries developed by expert programmers and an even larger ecosystem of users that combine these libraries into complex applications. So as one example, in the Python ecosystem, a typical machine learning application could load and preprocess some data using pandas, normalize it using NumPy, and then train a machine learning model over it using scikit-learn or some other ML library. So on one hand, this is great because users can leverage thousands of expertly developed libraries across many different domains to continue building powerful applications. However, an increasing downside of composing these existing software packages is that on modern hardware, composition is no longer a zero-cost abstraction in terms of performance. So to see why this is the case, let's look at the function call, which is the most ubiquitous interface for software composition today. So we'll look at how this interface works using a function that computes the logarithm of each element in a vector. So first, a developer specifies in the interface some arguments that are passed into the function via the stack. So if these arguments are large, they can be pointers that refer to values that reside somewhere else in memory. Next, the developer specifies some code that operates on these arguments. So generally, we'll have some code that loads data from memory, and then some code to process data. So in this case, we can actually use some fancy SIMD intrinsics to compute a logarithm over batches of data very efficiently. But the problem is, even though this function on its own is highly optimized, it turns out that the growing gap between memory bandwidth speeds and processing speeds actually makes composing functions like this worse and worse over time, because the interface requires each function to independently move values from memory into the CPU first. So to see this in a larger context, we can look at a simple NumPy example that composes functions like the one on the previous slide. So even though this example is in Python, each function is actually backed by an optimized implementation under the hood. So in this example, which is taken from a real workload that computes the Black-Scholes options pricing model, we first execute an element-wise multiply over two vectors, followed by an element-wise logarithm, followed by an element-wise addition. And because each function executes independently over in-memory values, the overall execution repeatedly scans these values from main memory rather than collectively operating on values that reside in, say, CPU registers or caches. This data movement between main memory and the CPU is a significant bottleneck on modern parallel hardware. And in fact, it can often be the dominant bottleneck in composing existing functions. So this is why software composition is no longer a zero-cost abstraction on modern hardware. This is a problem today because hardware trends are shifting the bottlenecks in today's applications. Specifically, compute throughput on new parallel hardware has been outpacing memory bandwidth. This plot shows the ratio of compute throughput to memory bandwidth over the past several decades for a typical server from each year. So in 1960, a computer usually spent the same amount of time moving data into a register and processing it. Today, that's certainly not the case due to parallelism from multi-core, SIMD, architectural pipelining, and so forth. This makes the function call interface increasingly efficient because even if the computation for each function is optimized, the movement of data between the functions is not. In addition, as the right side of this plot shows, new accelerators make this problem even worse because moving data into them is even more expensive. So a natural question is, do we really need a new way to combine software? Many of these problems are things that people have thought about and have proposed some solution for. So as an example, one strawman solution is to just use a monolithic system, such as TensorFlow and Spark, and allow these systems to optimize applications. However, this ignores thousands of developers that rely on that huge ecosystem of libraries. And it also ignores the millions of legacy applications that use these libraries already. So just as an anecdotal example, we hosted this data scientist from Google's Accelerated Sciences team at a seminar at Stanford. And he spoke about how he and many others rely on libraries such as scikit-learn and Xarray for applications ranging from drug discovery to weather modeling. Another possible solution is to just ask people to write optimized code. However, manually re-implementing functionality of existing libraries is just too difficult to do in general. And even combining libraries efficiently is not easy. So as another example, Intel's deep learning library called MKLDNN uses MKL under the hood. So MKL is this highly optimized linear algebra package that's developed and tuned for Intel processors. However, to make composing graphs of MKL operators efficient, MKLDNN actually has a ton of internal logic to partition values into pieces and call MKL functions on chunks of data to enable things like cache pipelining. So this is just another indicator that the interface between software has to change. So just to summarize what I've talked about so far, we kind of see three high-level challenges for software composition today. The first is that moving data between software components is increasingly expensive. The second is that hardware accelerators further complicate performance, not only because moving data into them is more expensive, but also because of concerns such as memory management or limited device memory. And the third challenge is that developers are increasingly sacrificing programmability for performance, even when using existing high-level APIs. So the research vision for my dissertation and this talk is to make software composition a zero-cost abstraction again. To this end, my thesis work revolves around building new interfaces for composing software on modern hardware. And the key idea that we utilize to do this is to use algebraic properties of software APIs in new interfaces to enable new optimizations. So as an example, an algebraic property could say that the loops inside two functions can be fused, or that data between two functions can be split and pipelined. We can then build systems around these properties to enable new optimizations such as loop fusion, data pipelining, or automatic parallelization, possibly underneath existing software APIs or without even having to change existing library code. So the approach I took during my dissertation work is to build three new interfaces with three new systems to leverage their properties. So the first two systems I'll talk about in this talk, weld and split annotations, focus on data movement optimization and automatic parallelization over existing library APIs. And even though these systems have the same focus, they offer drastically different design points for actually how to achieve this goal. And the third system I'll talk about, called raw filtering, changes gears a bit, and it focuses on I/O optimization during data loading. And this just shows that this idea of redefining composition interfaces is applicable across the software stack. So as a preview of some results from these systems, the left plot shows that Black-Scholes options pricing model workload I showed as an example a few slides back, but implemented using Intel MKL. So as a reminder, MKL is probably the fastest linear algebra package on Intel CPUs. Nevertheless, with Weld, we were able to accelerate this workload by 3x on 16 threads. And perhaps surprisingly, our split annotations interface also gave us similar results on this workload just by annotating black box functions with no library code changes at all. In the right plot, we're executing some queries from this database called census over JSON data in Spark. With raw filtering, which is a system I'll mention toward the end of this talk, we can accelerate these queries by up to 4x end-to-end by redefining the interface between data parsers and the upstream query engine. So in the rest of this talk, I'll introduce Weld, followed by split annotations, followed by raw filtering. And then I'll talk about some of the work that impact that this work has had, talk about some open source stuff, and then end with some concluding remarks. So the first system I'm going to talk about is Weld, which is a common runtime for data analytics. And most of what I'll talk about is work that was presented at CIDR 2017 and VLDB 2018. So Weld is motivated by a lot of the problems that I spoke about in the beginning of this talk. But just to recap quickly, the main problem it looks at is that there's this ecosystem of hundreds of existing libraries and APIs today, but combining these libraries is no longer efficient due to bottlenecks such as data movement. So as a concrete example, we benchmarked one particular workload that normalizes some images in NumPy and then applies a binary classifier on them in TensorFlow. Even though both of these libraries are implemented in C or C++ and are individually optimized, we found that there was a 13x gap between this and just handwriting a C++ application to perform the same task. So the question Weld asks is, can we enable existing APIs to compose efficiently on modern hardware? So Weld's approach for doing this is to use a common runtime targeted toward data analytics workloads. Libraries from different domains such as SQL, machine learning, and graph processing target this common runtime. And the runtime will optimize the workload end-to-end and generate code for CPUs, GPUs, or other kinds of parallel hardware. Under the hood, Weld has three main components. The first is a lazy runtime API that library developers use to submit work into the Weld runtime. The second is the Weld IR, or intermediate representation, which is a small functional programming language used to express the computation in each library function. And the third component is an optimizer that transforms the input Weld IR into an end-to-end optimized program. So just as a reminder, Weld primarily focuses on data movement optimization and automatic parallelization. So many of the design choices that we made in designing these components are influenced by that choice. In the rest of this section, I'll describe each of these three components in turn, starting with Weld's runtime API. The runtime API uses lazy evaluation to collect work across libraries. This is similar to APIs of other popular systems such as Spark SQL or Dask data frames, which also use lazy APIs. So as an example, say we have a user application with three Weld-enabled functions, lib1.f1, lib2.map, and lib3.f3. When the application calls these functions, they don't compute anything over their inputs. Instead, each function will use its inputs to generate an IR snippet representing its computation, and then it submits the snippets and any data dependencies to Weld using the runtime API. Weld internally tracks dependencies between individual IR snippets. When you actually want to compute a result, so this might be when you want to print out a computation or send it over the network, for example, Weld will join these IR snippets into a single combined IR program, use its optimizer to generate an optimized IR program, and then generate machine code. That machine code links with the parallel runtime, and that's what the data in your application actually interacts with. So the next question is, how do we actually express the computations in each library so Weld can effectively optimize them? And that's where Weld's IR comes in. So Weld's IR is used to express computations from each library, and it's designed to meet three high-level goals. The first goal is generality. We want it to be able to support a diverse range of workloads, ranging from linear algebra to graph processing. And we also want it to be able to support things like nested function calls, such as making one library function call inside of another. The second goal is the ability to express optimizations, with a particular emphasis on data movement optimization, such as loop fusion and loop tiling. And the final goal is explicit parallelism. Since this is an IR for modern hardware, it makes sense to make parallelism explicit in the language. So apart from some basic operators to do things like arithmetic and branching and so forth, Weld's IR has kind of two main constructs. The first is a parallel loop, which is used to loop over a data set in parallel. So that's pretty straightforward. And the second is a new concept called the builder, which is a declarative object to produce results from within a parallel loop. So when I say declarative object, I mean that a builder will say something like append items to a list or compute a sum, within the IR, but it won't actually specify a concrete implementation for how to do these things. So this lets builders have different implementations for different kinds of hardware. Builders have this additional constraint that says that reads from a builder are only allowed after all writes to a builder are complete. This allows us to implement builders using mutable state, even though builders are used in this parallel setting and within a functional IR. So formally, builders are based on this concept called linear types. So with just these concepts, we can actually use the Weld IR to capture a wide range of workloads, from relational algebra to the functional APIs of systems like Spark, to linear algebra, and most importantly, a composition of all these things as well. So to show you what Weld IR actually looks like, we can implement some functional operators with it. This is what a map operation looks like in Weld. A map function applies the function f to every element in data. To do this in Weld, we first create a builder called an appender, which appends items to a list when we write values into it. Next, we use the parallel for loop to iterate over the input data. Within the for loop, we use this merge operator to write values into the builder. This happens in parallel, and the builder can choose how to manage its own parallel state. Finally, after all writes are complete, we can use this result operator to finalize the builder into our output vector. So the result operation can again choose its own implementation, but generally it'll do things like aggregating partial per thread state, for example. A reduce operation looks similar, but it just uses a different kind of builder that aggregates a function or aggregates a value using an associative function. So Strawman and data parallel IR could have also just used map and reduce as first class operators instead of these lower level loops and builders. But it turns out that this design actually makes expressing some data movement optimizations easier, as I'll show with Weld's optimizer. The main goal of the optimizer is to remove redundancy caused by composing independent libraries and functions. As an example, excessive data movement is one form of redundancy because it's caused by redundant loads and stores of data from memory. The optimizer is architected as follows. First, the IR fragments from the runtime API are combined into a single program. Next, a set of rule-based optimizations remove redundancy by applying transformations to the IR programs. These are basically algebraic source-to-source transformations over the IR. Next, Weld contains an adaptive optimizer that can make data-dependent decisions based on, say, branch probabilities. So I actually won't talk about this component in this talk, but you can see our paper on Weld for more details on it. Finally, the optimized IR is sent to a backend for code generation. So the rule-based optimizations are the ones responsible for removing redundancy in Weld code. So as an example, here's a typical IR program that a library such as NumPy would generate. So the corresponding NumPy code that would generate the Weld IR is shown on the right. So because each line of code is generated by a separate function called a NumPy, there are some clear inefficiencies in this code. First, there's an unnecessary materialization of temp. We only care about the output res1, but both NumPy and as a result, the generated Weld code will materialize an intermediate output and then scan this output from main memory to produce the final results. There's also two distinct scans of data to produce res1 and res2. And finally, we're also potentially missing optimizations such as vectorization and things like output size inference. After running the optimizer, this is what the final IR program looks like. The most obvious change is that we've replaced map and reduce, which are just macros in Weld, with builders and for loops. However, there's some other notable optimizations that took place as well, which loops and builders actually facilitate applying. The most important optimization Weld applies is loop fusion, where a loop can be pipelined when its input is the output of another loop. So notice that in the optimized code, we're never actually materializing that temp vector anymore. Instead, in the body of the for loop, we're computing x times x, which is what the temp vector was storing, and we're directly merging that into a merger, which computes the final reduction that we want. This is the key data movement optimization in Weld, because it removes unnecessary memory allocations as well as unnecessary loads and stores from main memory. We only need to perform one linear scan of the input to compute the final output in this case. Weld can also apply other optimizations, such as SIMD vectorization. So of course, these are things that compilers today do already, but in many cases, it's actually easier, or at least faster for Weld to do them instead of a more general compiler such as LLVM, since loops here are already assumed to be parallel. So you just have to do less static analysis to prove that these things are safe to do. Okay, so jumping into some results, we did a partial integration of Weld with several libraries, NumPy, Pandas, TensorFlow, and Spark SQL. We evaluated on 10 data science workloads from various online sources, such as Kaggle, but we also evaluated Weld on micro benchmarks against existing specialized systems. So I'll talk about a subset of these results in this talk. The main thing Weld enables is optimization across different libraries and functions. So in this workload, we're loading and whitening images in NumPy to normalize them for classification. And then we're running a binary logistic regression classifier in TensorFlow. We're also running with TensorFlow XLA in this workload. So XLA is this linear algebra compiler to perform optimizations such as operator fusion on TensorFlow graphs. Despite this, on a single thread, Weld can actually accelerate this workload by around 3.5x by fusing operators across libraries. So the original workload writes intermediate results despite the XLA optimizations, because NumPy can't take advantage of XLA. With Weld, since both libraries are Weld enabled, we can perform loop fusion across libraries and pipeline the pre-processing with the classification. Since Weld can also automatically parallelize any loop, Weld can also parallelize the whole computation on 8 threads. In contrast, only the TensorFlow part is parallelized in the original version. So this gives a total 13x speedup in this case. Another key design point with Weld is that it can be integrated incrementally with libraries. And Weld-enabled code works automatically with native library code because of the runtime API design. So in this plot, we're running that Black-Scholes options pricing model again in NumPy. The x-axis shows the number of operators from this workload that we ported to Weld, and the y-axis shows the resulting runtime. And the operators reported in order of importance. So the operators that take the most time in the workload reported first. The key takeaway here is that porting the most important operators first give you most of the benefits. This implies that developers can Weldify their libraries by focusing on more expensive operators and still see a substantial performance benefit. You don't have to go through your entire library before seeing any gains at all. And finally, to demonstrate that Weld can provide good raw performance, we also benchmarked it against specialized systems in several domains, just machine learning, graph processing, and relational algebra. So this is a result on a few queries from the TPCH benchmark, which is a SQL benchmark, comparing Weld's performance against Hyper, which is a state-of-the-art in-memory SQL database that uses code generation under the hood. And we're also comparing against some handwritten C++ implementations that we and a few grad students from MIT's database group implemented. So across the board, Weld's compiler generates code that's competitive with both Hyper and the handwritten baseline. And all these baselines are also open source, as are the other benchmarks. So people can try to submit, faster implementations of the baselines. And if they outperform Weld, you can, find new ways to improve the compiler as well. And finally, we also wanted to study the impact that each optimization has in Weld on our whole suite of workloads. So to do this, for each workload, we turned off each optimization one by one and measured the resulting slowdown compared to having every optimization on. So in this figure, each box shows the slowdown from turning off the optimization in the corresponding column. So this first column shows all optimizations enabled. And right off the bat, you can see that the most impactful optimization by far is this loop fusion optimization that I talked about earlier across the board. This is the optimization that reduces data movement by pipelining the output of one computation with the input of another by fusing their loop bodies together. This supports the idea that data movement optimizations are the most important ones in a multi-threaded setting and contribute to most of the speed up. So we'll actually revisit this fact when I talk about split annotations in a couple of slides. So just to mention a bit of prior work, Weld obviously builds on a ton of prior work ranging from runtime code generation in databases to languages for parallel hardware to things like monad comprehensions. The main thing that's new about Weld is this interface that allows us to do the optimization studied by previous systems on top of existing library APIs and enable them across library functions with this new composable API and IR. Weld's also the first system that we know of that can do these optimizations in existing libraries incrementally. So just to fill out this table a bit, the interface that Weld proposes is this IR to extract the parallel structure of library functions. And the system backing it is basically this compiler to enable data movement optimization and parallelization. So the Weld work showed that compiler-based interfaces can give some great performance results, but they also have some usability limitations. So Weld also showed that the data movement optimizations in particular are by far the most impactful ones, especially for these data analytics workloads. The next project I'll talk about, split annotations, addresses some of the shortcomings of a compiler-based system while enabling some of the same data movement optimizations over existing libraries. So this is work that we presented at SOSP 2019. The main problem with a compiler-based system like Weld is that it requires a ton of developer effort to use in a real setting. In particular, you need to replace every function to use a compiler intermediate representation to see any benefits. And the IR may not even support all the optimizations that are present in already hand-optimized code. So just to give you a snapshot of the effort required to use a compiler-based system, Weld needs hundreds of lines of code to support kind of a rudimentary integration with NumPy and Pandas. And then you, of course, need to write a snippet of IR code for every single function beyond that that you want to support as well. And because of their complexity, JIT compilers will often see issues like this. So in the top example, this tracing JIT compiler for Python called Numba failed altogether because it didn't recognize an operator that appeared in the application. And adding support for it would likely be a multi-week effort. In the bottom example for TensorFlow XLA, turning on compilation actually made the performance worse. In this case, the developer stated that some operators are just expected to be slower than hand-optimized ones, since it's too difficult for the compiler to generate code that matches an expert's implementation in all cases. So split annotations are a new interface for enabling the data movement optimizations and automatic parallelizations enabled by compiler-like interfaces, but without having to modify existing library functions. The key idea in split annotations is pretty straightforward. It's that you split data to pipeline and parallelize it across a series of functions. So to see what execution looks like without essays, let's look at that snippet from Black-Scholes again. So in this first function is called, the entire inputs are scanned from main memory to produce a result. When we call subsequent functions, reused values are scanned again entirely from main memory, assuming that the inputs are larger than the CPU caches. So this causes the data movement bottleneck that I've been harping on about. With essays, we change the way that this execution carries out. The system will build an execution graph, and we can keep data in the CPU caches by only passing cache size splits to each function in the execution graph. So rather than passing the entire inputs to this first function call, we only pass splits of the inputs that collectively fit in the CPU caches. We can then pipeline these splits across all the function calls in the execution graph, and then we can just go through and process each of these splits in turn. And we can get parallelism by parallelizing over the split pieces. So as an example of what a split annotation actually looks like, let's look at a symbol function that adds two vectors element-wise in Intel MKL. So this is what the split annotation for this function looks like. So just with this annotation and a small API to go with it, we get some pretty nice benefits compared to JIT compilers. First, we don't need to make any intrusive library code changes to this library to use the annotation at all. Second, we can reuse an optimized library function implementation that's already there instead of having to rely on a compiler to generate code that might be as good or might not be. Finally, we don't even need access to the library to use the annotation. As an example, MKL is a black box library. It's closed source, so we don't actually have access to the source code, but we can still go through and annotate it and get the benefits of essays. Because of these benefits, essays can even outperform compiler-based approaches in some cases. So this plot shows the Black-Scholes workload again for the last time, I promise, this time implemented using Intel MKL. So here the MKL line starts to taper off around 4 threads because of the data movement issue. So as we add more threads, more and more time is spent in just waiting from loads from main memory. And after a point, adding more threads doesn't help because we're just bound on memory bandwidth. With Weld, we see better scaling, but in this particular case, Weld's per operator performance is worse because MKL is already highly optimized, and Weld's compiler just doesn't generalize code that's as good as an expert's implementation. With split annotations, we get the best of both worlds. We can still leverage the optimized MKL implementation of each function, but we also get the data movement optimizations of Weld, and thus get good scalability. So overall, we get a 5x speed up by reducing data movement in this case. So there's several challenges in designing essays for real libraries. The main challenge is defining how to split the data passed into each function and ensuring that data passed between two annotated functions is actually safe to pipeline. This means ensuring that operating over split data will produce the same result as operating over entire inputs without pipelining, assuming that each function is annotated correctly given our interface. The second challenge is building a lazy execution graph of the annotated functions transparently. Since we don't want developers to modify their libraries, we want to demonstrate that lazy evaluation is possible without intrusive code changes. So recall that with Weld, we had to use this runtime API to build up this task graph, but we don't want to do that here. And the final challenge was designing a runtime to actually execute these arbitrary functions in parallel. So I'll primarily talk about this first point in this talk. And you can see our paper for implementation details on how we did these other two things. So how do essays enforce safe pipelining? Let's first talk about what safe pipelining actually means with a concrete example that uses two matrix functions. So say we have two functions that both iterate over the matrix in row order. In this case, it's okay to pipeline data between the functions because we can split the matrix up by row and pipeline the rows between the two functions. At the end, we'll have correctly processed the full matrix. But now say we have one function that iterates over the matrix by row and another that iterates by column. It's actually not safe to pipeline data between these two functions, because if we were to pipeline rows, the second function would iterate the matrix by column and perhaps read some data that it expected to be updated by the first function. So in short, there's this semantic mismatch between the first case where pipelining is allowed and the second case where it isn't. Our annotation interface needs to be able to distinguish between these cases at runtime, since users can arbitrarily compose annotated functions. So essays use a type system to enforce safe pipelining. The building block of this type system is a new concept called split types, which uniquely define how arguments and return values of a function are split. As an example, here's that VD add function I showed a few slides back. Its annotation assigns a split type to each of its function inputs, and each split type defines uniquely how each argument is split. So to define how to split values, split types can have runtime values as parameters. As an example, array split partitions array into regularly sized pieces. To uniquely define a partitioning, we need both the length of the array n, but also the number of pieces that the array is split into, which the annotation denotes as k. So k is actually a value that the runtime will set automatically based on things like the CPU cache sizes, but we'll just put it here for completeness. So as an example, an array split type with n equals 1000 and k equals 10 uniquely defines an array of length 1000 split into 10 pieces. And this is a different split type from, say, array split with n equals 1000 and k equal to 100. So given these split types in each annotation, we can enforce safe pipelining by adding constraints on when a function can operate over split data. So notice that we've assigned the same split type array split to each of the array inputs for this particular function. This means that our function will only call VDAdd on split data if at runtime the inputs to VDAdd are split in the same way. In addition, we can only pipeline data between two functions if the data passed between the two functions also have the same split type. So as a more concrete example, let's look at splitting matrices in NumPy, where functions actually let you control whether they occur by row or by column using an axis argument. So we can encode this in a matrix split type with a Boolean axis as one of the parameters. So if axis is 0, the function is by row, and if it's 1, it's by column. At runtime, when a function is called, these parameters are initialized with values in the split type. This lets us distinguish between the two cases that I mentioned earlier. In the left example, the split types match because the two functions assign the same split type to the matrix. This lets rows of the matrix be pipelined between the functions. In the right example, the split types don't match because of the axis. If the first function is operating over split data already, it needs to merge the split pieces before calling the next function. So how do annotators actually write essays? First, you define a split type, such as array split or matrix split. And this is just logically deciding how data in your library should be split. Next, you write a split function and a merge function for the type. So this is some code you submit to our system that defines how values should physically be partitioned. And finally, you annotate functions using the split types that you've defined. So Mozart is our system implementing essays and its runtime. Developers write annotations and then use a command line tool to generate a wrapped library which applications call into. Internally, the wrapped library calls into a client library that's responsible for registering calls to annotated functions with a lazy task graph. The client library also determines when the task graph should be evaluated. So in our C and C++ implementation, we do this using memory protection. And in Python, we use metaprogramming to inject lazy evaluation. And you can see our paper more details for precisely how these things work. Usually library developers don't need to make any changes at all. And you can see our paper again for the caveats of when you need to make code changes and so forth. After the client library decides to evaluate the task graph, the runtime will check split types, split data, and execute functions in parallel. Okay, so jumping into some results again. We integrated split annotations with a subset of 5 libraries: Intel MKL, NumPy, Pandas, Spacey, which is a Python natural language processing library, and ImageMagick, which is a C image processing library. Our integrations demonstrate that essays support a number of data types and operators, ranging from arrays and tensors to operators like data frame joins to grouping aggregations to image processing functions. So one of the main motivations for essays was that enabling data movement optimizations with a compiler-based approach was too difficult to do in practice. To show that using essays really is easier than using a compiler, this table shows the number of lines of code it took to use split annotations for each library we annotated. The most telling line in this table is the pandas integration. To support essays for the same 15 functions that we supported with Weld, it took us almost 20x less code because we just needed to write a couple of split and merge functions to define how to split data frames, and then add annotations to these existing functions. Anecdotally, with Weld, we had to implement things like data marshalling to support data into the runtime, and we also had to write IR code to re-implement each function. So while this does give us some performance benefits that essays can't provide, as I'll show in the next few slides, essays can actually get pretty close in many cases. So it turns out that essays can actually match JIT compilers in some cases. The workload on the left simulates planetary motion in the galaxy over time using NumPy. So we're comparing split annotations with standard NumPy and several compilers that exist over NumPy's API, including Weld. As you can see, essays actually get pretty close to the best performing compilers in this case, and provide a 4.6x speedup over NumPy on 16 threads by applying that pipelining optimization for data movement, and also enabling parallelization by parallelizing over split pieces. The right workload is a pandas workload with more complex operations. So it performs a join followed by a grouping aggregation, and then constructs a pivot table. The workload actually doesn't have many components that can be naturally pipelined, but essays can still speed it up by matching Weld's performance on it by parallelizing each operator individually. Finally, essays can also provide speedups over libraries that are highly optimized. So the left workload here implements a differential equation that simulates ripples in a pool of shallow water. Even though MKL supports parallelism and is highly optimized, the pipelining that essays enable speed up this workload by around 3x on 16 threads. The right workload implements an image filtering pipeline over a large image. Again, essays basically just enable splitting and pipelining chunks of the image across many image operators and enable a 1.8x speedup on 16 threads. So even though these speedups seem relatively modest, it's important to remember that these are libraries that have been optimized over many years, are written in C, and already support parallelism. So the fact that we can do this just by adding some annotations on the functions is significant and demonstrates that the interface for composition really does matter. So across the 15 workloads that we benchmarked, essays perform within 1.2x of all the compilers we compared against in 9 workloads. They outperformed all compilers in 4 workloads, and they were outperformed by compilers by more than 20% in 2 of our workloads. So they were up to 6x lower. And this happens when code generation matters. So when you're, for example, compiling interpreted Python. So like Weld, essays build on a large body of prior work. The main technique of pipelining batches of data that collectively fit in the CPU caches is inspired by database vectorization. And there are other interfaces such as Numba that use annotations for code generation. Essays are the first system to use this annotation-based approach to apply these optimizations across independently written libraries and functions. Okay, so filling out this table a bit more, the interface that split annotations propose is these annotations to define how to partition function inputs, and the system is a runtime to pipeline data among unmodified library functions. Okay, so the final project I'll talk about very briefly is called raw filtering, and it changes gears a bit. It focuses on optimizing data loading and data processing frameworks by redefining the composition interface between parsers and query engines. The premise of this work is that it turns out parsing is a huge computational bottleneck in big data systems, especially over data formats such as JSON and CSV. This is largely because of the interface to these parsers. A query engine will load a raw byte stream of data and pass it to the parser, and the parser will parse every single record in the raw data set for processing. This happens even if the record will be discarded by the query later on. So one opportunity that we saw for optimizing this is that many exploratory analytics workloads that operate over formats such as JSON have very high query selectivity, meaning that the query will use filters to discard much of the loaded data. This plot shows the query selectivities on real workloads for queries over JSON and CSV data at Databricks and over this network database called Census. So overall, 40% of the customer queries at Databricks select less than 20% of the data in the final result, and 99% of the queries in Census select less than 0.001% of the data. So we can again treat this as an interface problem. Parsing is expensive and wasteful because the parser has no knowledge of the query filters that come after it. So the question is, how can we exploit this high selectivity to accelerate parsing? So the key idea in this work is to filter before parsing data by pushing query filters into the parser itself. We built a system called Sparser that does this by using fast filtering functions over a raw byte stream to discard data. So the filtering functions have false positives, so they may let through data that the query engine may later throw out, but never false negatives. So we'll never throw out a sequence of bytes that would later be parsed into a record that passes the query filter. So the result of these filtering functions is a smaller raw data set that we can then parse using the full parser. However, even these small filtering functions are composable. We can chain them to get a smaller and smaller raw data set, and at the end, we can use the full parser to get records and run the actual query. Our system uses an optimizer to decide how to choose which filtering functions to use to balance the overhead of using this technique with the actual cost of doing the parsing. And you can see the paper for more details on how it all works. Because parsing is so expensive, restructuring the parser in this way can lead to significant end-to-end speedups. So on this set of 9 real queries from the census data set, over 650 gigabytes of JSON data, we were able to get a 4x end-to-end speedup in Spark by using our system to toss out data before even having to parse it. So the interface here is basically these composable filters that can have false positives with the property that they can basically be composed to decrease the false positive rate as you compose the filters. And the system is this library for accelerating I/O of serialized data. So hopefully I've convinced you that new composition interfaces can improve performance fairly significantly on modern hardware, even over existing library APIs. A lot of this work has had impact both in industry and via adoption in other labs. So Weld is being used at NEC to target a new vector accelerator. They're actually using the IR to bridge their accelerator's compiler with high-level APIs such as Pandas and NumPy by developing a new hardware backend for Weld. Weld was also prototyped at Databricks for a new SQL execution engine there, and it's being used at labs around the world for other research as well. We published essays recently, but there's already some ongoing work at Stanford to extend it to work with GPU libraries. We're also exploring using similar ideas to enable other kinds of algebraic optimizations beyond pipelining to existing libraries. And finally, Teradata and Google have both prototyped raw filtering internally. Teradata is trying it for queries over JSON data, and Google has actually tried it for making processing queries over protobuf faster. Okay, so jumping into some acknowledgements, I don't think anyone can go through the PhD alone, so I have a number of people to thank for helping me make it this far. First, thanks to my committee, Keith, Christos, Mendel, and John. I know you guys are super busy, and I appreciate the fact that you're able to make time for the defense, and if you're on the reading committee, also for reading and providing feedback on the dissertation. None of this, of course, would have been possible without my advisor, Matej. Matej and I, as he said, first worked together at MIT 5 years ago, and ever since I've met him, he's been both a great mentor and just a very comforting presence in the lab. He's always been available to provide advice on anything from how to structure a piece of code to how to think about a new research problem to where you can find the best milk tea in a 10-mile radius, though I don't think we found anything better than Asha at Berkeley yet. And I think one of the best things about Matej is just how humble and kind he is. So my friends and lab mates and I are always amused when Spark Summit comes around, which we've also noticed is highly correlated with when he gets a haircut, by the way. And literally thousands of people see him as this messiah of big data. Because when he shows up to our group meeting and lunches armed with a fresh set of puns, you would never really know it. The only things that he reveals about himself is that he's a fantastic researcher who's dedicated to his students. So I've really enjoyed working with you, Matej. And then finally, I'm very grateful for the support of all my lab mates, from playing board games together to gossip sessions in the middle of the day, to feedback on papers and talks. So Cody, Daniel, Deepti, Edward, Fyodor, Kaishang, Keshav, Keshin, Peters, Bela Sandcraft, Pratiksha, and Sahana. Thank you. I'm gonna miss you guys. To my office mates, Deepak, Faraz, and James, who made grad school fun even during the lowest points, for teaching me a lot about sports, which I knew nothing about 4 years ago, and also just tolerating 4 years of terrible jokes. And then thanks to all my friends outside of Stanford, Akshay, Abro, Jeff, Neil, Rohit, Stephanie, Sagar, Sahil, and Yuval. You guys are definitely responsible for keeping me sane when I need to think about something other than research. And then of course, I would not have enjoyed grad school as much as I did if it weren't for my wife, Paroma. As Matej said, the two of us met during grad school visit days, and before we started dating, we ended up on different sides of the country. But we didn't let that get in the way, and only a year later, we were lab mates at Stanford, going from being 3,000 miles apart to 30 feet apart. So she actually worked, I think, 3 doors down from me. And her support has made this one of the most memorable times in my life. And finally, I want to thank my family, my parents, Anjali and Prasad, my sister Ishani, my aunt and uncle Trupti and Sorja, and my 2 little cousins Shreya and Pusha, who have all collectively been responsible for giving me an escape on weekends, but also collectively keeping me smiling for the last 26 years. And with that, I'm happy to take questions. Thanks.
All right.
Clapping.
Yeah. All right. So yeah, I think this is time for the public questions part of it. So anyone can ask questions. If we have too much congestion on the questions, we can also use the chat. So any questions from the audience for the public part? Yeah, I guess it's hard to get these types of questions over Zoom, or maybe Shoumik answered all the questions. Maybe
I'll
I'll
also
ask...
leave questions. Yeah, sure, go ahead, Matej.
Oh, go ahead, yeah. Yeah, you can also put them in the chat if you want. Yeah, maybe I'll ask one question in this part, which is the like the things you showed, are they all, distinct? You either use this or that, or can you also combine them? Like what if you do want to write a compiler and have some existing functions that you annotate?
Yeah, that's a good question. So I think, yeah, it's definitely possible to combine some of these techniques. So I think the long-term vision for all this work is to actually have it be combined in some way. So one example is you could provide an annotation that has these split types, but then you can also optionally maybe add like a snippet of weld code into it or something. And the underlying runtime that drives these things would be the same, and there'd be some planner that decides whether you want to compile like this particular function or just call into some existing thing by splitting it. So they're definitely not like disjoint techniques. I think the real kind of solution is somewhere in the middle. It's not like you only use existing code or you only have to like recompile everything. It's probably some middle ground.
Okay, cool. Okay, any other questions? Looks like we have one in the chat.
Yeah, so the question is, where do you plan on taking this in the future? So one thing is kind of just combining these different techniques to build a more, full system that's easier to use in some sense. We also have some other projects going on to apply other kinds of optimizations over existing libraries. So right now, split annotations basically just enable parallelization and pipelining. But in theory, you could also, do more database style optimizations as well. So one example is if you have a bunch of library functions, there's probably more than one way to use that library. So you could probably, write rules over your library to kind of transform one use of your library into another. That might be more efficient, for example. So like a really simple example is if someone's writing a loop over a dot product, that can more efficiently be represented as like a matrix multiply, because then you can do things like loop blocking. So how can you do those things kind of automatically without having the developer know, like which library function is more efficient than which other library function?
I have a question.
Can you hear me?
Yeah.
I guess one common feature of all of these projects is that you've sort of taken an existing library and you've added something on top of it to improve that library's functionality or interoperation with other libraries. I was just wondering if you learned any or have any recommendations for library writers so that they can improve their own libraries, like before you add these things on top of them to improve the interop. So when you're writing the library, what should we be thinking about, or like lessons from these projects for library writers?
Yeah, that's a great question. I think there's kind of two conflicting points of view. One point of view is basically you just write like these really tiny kind of like kernels or kind of these really simple building blocks that systems like, split annotations can take advantage of to kind of compose efficiently. And the other point of view is, you make your functions kind of as specialized as possible so that you can kind of pack all the optimizations in there yourself. So I don't really know which of those is correct. From like a purely like academic systems point of view, I think that the first way of doing things is more interesting, where you kind of write each library as these small building blocks, and then you have like some super general system to like combine these building blocks into applications that are very efficient. But yeah, I guess I don't know like what I would recommend to like new library writers, just because we don't really have a system that works like that in the most general cases yet.
Makes sense. Thanks.
Okay, any other questions for the Spark? Okay, so if there aren't any more questions, we can go to the closed door part of the defense, and I think Shoumik has a separate meeting. Oh, is there something?
Yeah, Matei, can we take a 5-minute bio break?
Yeah, we could do that, yeah. So we can just join the closed door meeting. So yeah, thanks again, Shoumik, and we'll see you soon.
Thanks everyone for coming.
Yep. See you folks in the other meeting.